Hello, my name is Daniel O'Connor, and this is my lab on constant velocity. So the methodology and how I collected this data was I made a video of an object moving in constant velocity, and I analyzed it in Tracker, as seen here. I analyzed it frame by frame, and then I got this nice data table. Okay, so then I found the average velocity using a formula I will show. And using this average velocity, I created a model in GlowScript of this motion. And then with those results from the model in GlowScript and the ones from Tracker, I compared them to see if there were any differences. So this is the average velocity formula that I used. But in reality, this is only calculating the initial velocity. But since our model is in constant velocity, the initial velocity is equal to just the velocity over the entire time interval. So as you can see, I started at 1.8 seconds and I went to the very next frame of 1.808 seconds to calculate this average velocity, which is equal to the initial velocity and is just the velocity in general because it's constant, meaning there's no net forces or accelerations happening on this object. So as you can see, our system is this object moving with a velocity v. And then our surroundings are especially the track, which it is riding on, which there is a force of friction, but it is minimal here. So now let's talk about Newton's second law, which as you can see relates acceleration to the net force and mass. So acceleration is the change in velocity over time. So as you can see, once we simplify this out and take and integrate it, we get this very nice iterative formula. V final is equal to V initial plus acceleration delta t. And then we just substitute in for acceleration here. And this is actually the formula we used in the GlowScript code to find the velocity of the ball. But we know that the net force on this object is 0. So really this is just ball.vel is equal to ball.vel. And that is the same here. It's just velocity final is equal to velocity initial because the velocity is constant, meaning there's no change in velocity, meaning there's no acceleration or net force. So here we get an even more useful equation. So if you look, velocity is the change in position over time, or dr/dt. And if we integrate this, we get an iterative formula of position final is equal to position initial plus v delta t. So as you can see, we use this in GlowScript, where the ball's position is being added to the velocity times delta t. And this is an iterative formula, so it is in the while loop. And the ball's velocity is constant, so really the only thing changing is delta t. And as a result, the ball's position changes. Here we have a ball object, a trail object, and an origin. And then we plot these on position versus time and velocity versus time. Here we have the ball's mass, which is 1, which really doesn't matter because there is no net force. But these do matter. These are the initial conditions. We have time is at 1.8, which is the initial time I analyzed in the Tracker video. So just to keep things consistent, then we have this position and this velocity, which is constant, delta t meaning the change in time. And then here we have the while loop, which is less than 2.633 seconds because that's the final time. And then we have these two iterative formulas. And as you can see, the net force is 0. So here it's just going to be ball.vel is equal to ball.vel. Then we advance the clock and finally plot this. So as you can see, we put this data into Google Sheets to create this model, this graph. And as you can see, the R-squared values are 1, meaning this model is a very good predictor of the experiment. And this can be due to the fact that the total time taken was only 0.833 seconds, meaning these forces didn't have enough time to take that much effect. Like the frictional force didn't really slow down the object that much because of how low the time was. Plus, we started 1.8 seconds after I pushed, so this could have already been diminished by this frictional force.